Except for hydrogen, all electrically neutral atoms contain more than one electron, with the number given by the atomic number Z of the element. In addition to being attracted by the nucleus, the electrons repel each other. This repulsion contributes to the total energy of the multiple electron atom. As a result, the one electron energy expression for hydrogen, En equals negative 13.6 electron volts times Z squared divided by N squared, does not apply to other neutral atoms. However, the simplest approach for dealing with a multiple electron atom still uses the four quantum numbers N, L, Ml, and Ms. Detailed quantum mechanical calculations reveal that the energy level of each state of a multiple electron atom depends on both the principal quantum number N and the orbital quantum number L. In this energy level diagram, we see that the energy generally increases as N increases, but there are exceptions, as seen here. Furthermore, for a given N, the energy also increases as L increases. In a multiple electron atom, all electrons with the same value of N are said to be in the same shell. Electrons with N equal 1 are in a single shell, sometimes called the K shell. Electrons with N equal 2 are in another shell, the L shell. Those with N equal 3 are in a third shell, the M shell, and so on. Those electrons with the same values for both N and L are often referred to as being in the same subshell. The N equals 1 shell consists of a single L equals 0 subshell. The N equals 2 shell has two subshells, one with L equals 0 and one with L equals 1. Similarly, the N equals 3 shell has three subshells, one with L equals 0, one with L equals 1, and one with L equals 2. In the hydrogen atom near room temperature, the electron spends most of its time in the lowest energy level, namely in the N equals 1 shell. Similarly, when an atom contains more than one electron and is near room temperature, the electrons spend most of their time in the lowest energy levels possible. The lowest energy state for an atom is called the ground state. However, when a multiple electron atom is in its ground state, not every electron is in the N equals 1 shell in general, because the electrons obey a principle discovered by the Austrian physicist Wolfgang Pauli. The principle is called the Pauli exclusion principle and is stated as follows. No two electrons in an atom can have the same set of values for the four quantum numbers N, L, Ml, and Ms. Suppose two electrons in an atom have three quantum numbers that are identical. N equals 3, Ml equals 1, and Ms equals plus 1/2. According to the Pauli exclusion principle, it is not possible for each to have L equals 2, for example, since each would then have the same four quantum numbers. Each electron must have a different value for L, for instance L equals 1 and L equals 2, and consequently would be in a different subshell. With the aid of the Pauli exclusion principle, we can determine which energy levels are occupied in the electrons in an atom in its ground state, as we now demonstrate. Suppose we want to know which energy levels in this diagram are occupied by the electrons in the ground state of hydrogen, 1 electron, helium, 2 electrons, lithium, 3 electrons, beryllium, 4 electrons, and boron, 5 electrons. We start by noting that, in the ground state of an atom, the electrons are in the lowest available energy levels. Consistent with the Pauli exclusion principle, they fill those levels from the bottom up, that is, from the lowest to the highest energy. As the dot indicates an electron occupying a level, the electron in the hydrogen atom is in the N equals 1, L equals 0 subshell, which has the lowest possible energy. A second electron is present in the helium atom, and both electrons have the quantum numbers N equals 1, L equals 0. However, in accord with the Pauli exclusion principle, each electron must have a different spin quantum number, Ms equals plus 1/2 for one electron, and Ms equals negative 1/2 for the other. Thus, the drawing shows both electrons in the lowest energy level. The third electron that is present in the lithium atom would violate the exclusion principle if it were also in the N equals 1, L equals 0 subshell, no matter what the value of Ms, since only two values of Ms are possible. Thus, the N equals 1, L equals 0 subshell is filled when occupied by two electrons. With this level filled, the N equals 2, L equals 0 subshell becomes the next lowest energy level available and is where the third electron of lithium is found. In the beryllium atom, the fourth electron is in the N equals 2, L equals 0 subshell along with the third electron. This is possible since the third and fourth electrons can have different values for ms. With the first 4 electrons in place as just discussed, the fifth electron in the boron atom cannot fit into the n equals 1, L equals 0, or the n equals 2, L equals 0 subshells without violating the exclusion principle. Therefore, the fifth electron is found in the n equals 2, L equals 1 subshell, which is the next available energy level with the lowest energy, as we see here. For this electron, ml can be -1, 0, or +1, and ms can be +1/2 or -1/2 in each case. However, in the absence of an external magnetic field, all 6 possibilities correspond to the same energy. Because of the Pauli exclusion principle, there is a maximum number of electrons that can fit into an energy level or subshell. We just showed that the n equals 1, L equals 0 subshell can hold at most 2 electrons. The n equals 2, L equals 1 subshell, however, can hold 6 electrons because with L equals 1, there are 3 possibilities for ml, -1, 0, and +1, and for each of these choices, the value of ms can be +1/2 or -1/2. In general, ml can have the values 0, plus and minus 1, plus and minus 2, all the way up to plus and minus L for 2L plus 1 possibilities. Since each of these can be combined with 2 possibilities for ms, the total number of different combinations for ml and ms is 2 times 2L plus 1. This, then, is the maximum number of electrons the Lth subshell can hold, as summarized here. For historical reasons, there is a widely used convention in which each subshell of an atom is referred to by a letter rather than by the value of its orbital quantum number L. For instance, an L equals 0 subshell is called an S subshell. An L equals 1 subshell and an L equals 2 subshell are known as P and D subshells respectively. The higher values of L equals 3, 4, and so on are referred to as F, G, and so on in alphabetical sequence as summarized in the table. This convention of letters is used in a shorthand notation that is convenient for indicating simultaneously the principal quantum number n, the orbital quantum number L, and the number of electrons in the NL subshell. For example, consider the shorthand electronic configuration 2p5. In this case, the principal quantum number n corresponding to the shell is equal to 2. The quantum number L of the subshell is denoted by the letter P, which corresponds to the L equals 1 subshell. Finally, the number 5 in this notation refers to the total number of electrons in the L equals 1 subshell. With this notation, the arrangement or configuration of the electrons in an atom can be specified efficiently. For instance, we found that the electron configuration for boron has 2 electrons in the n equals 1 L equals 0 subshell, 2 in the n equals 2 L equals 0 subshell, and 1 in the n equals 2 L equals 1 subshell. In shorthand notation, this arrangement is expressed as 1s2, 2s2, 2p1. The table gives the ground state electron configurations written in this fashion for elements containing up to 13 electrons. The first 5 entries are those we already worked out. Each entry in the periodic table of the elements often includes the ground state electronic configuration. Here we see the periodic table entry for argon. It shows the atomic symbol, the atomic number Z, and the atomic mass. To save space, only the configuration of the outermost electrons and unfilled subshells is specified using the shorthand notation just discussed. Originally, the periodic table was developed by the Russian chemist Dmitry Mendeleev in the late 1800s on the basis that certain groups of elements exhibit similar chemical properties. There are 8 of these groups, plus the transition elements in the middle of the table, which include the lanthanide series and the actinide series. The similar chemical properties within a group can be explained on the basis of the configurations of the outer electrons of the elements in the group. Thus, quantum mechanics and the Pauli exclusion principle offer an explanation for the chemical behavior of the atoms.